Hello, I'm Wonil from Penn State University. In this presentation, I'm going to talk about a resource partitioning problem in flash memory. Let's get started. Flash memory technologies are getting mature. Specifically, more and more flash memories can be integrated into a single system. As a result, we are now enjoying high capacity and high bandwidth flash storage systems. Correspondingly, flash use cases are also changing. Compared to the cases where only one single workload uses a whole flash system, we increasingly see the scenarios where multiple workloads are consolidated on a single flash storage system. Let us consider a consolidated system that is provisioned in a cost-conscious manner. In general, in such a system, demand is higher than supply. That is, needs of users exceed available resource capacity. So any form of resource allocation is required. For resource allocation, there are two canonical concepts, priority and fairness. For priority, we can adjust the relative importance of users. And when the priorities are identical, fairness can offer principled ways of resource partitioning. Consolidated flash systems are also facing such demand-supply mismatches, and they need fair resource allocation. There have been works on fair allocations of conventional resources, for example, storage capacity partitioning and bandwidth partitioning. In this work, we are interested in a flash-specific resource, namely device lifetime. The lifetime resource is non-renewable. That is, device dies when the resource is exhausted. So, there have been a large body of works on lifetime saving. However, to our knowledge, there have been no prior works on lifetime partitioning. Before going ahead, let me introduce a conventional way of quantifying device lifetime. A flash memory consists of a lot of pages, which is a base write unit, normally ranging from 4 to 16 kilobytes. Since data overwriting is not allowed in flash memory, the data can be written only into a clean page, and the page must be erased to update the data. Unfortunately, such repeated write and erase operations wear out the pages. So, vendors normally specify a limited number of write and erase operations for their flash lifetime. In this work, as a proxy of device lifetime, we use the number of page writes a device can handle. Now let me define our target problem, fair write allocation. First, total write budget is prescribed by administrator. Then assuming that there is no change in workload consolidation scenario, workloads are given. Then the total write budget is divided to the workload. Here, what is fair division among possible write allocations? In solving the write allocation problem, we face various difficulties. First, there is a hidden write contributor. To allocate write, we need to estimate the write demand of each workload. And it is easy to predict the number of writes each workload directly issues. But there's another write source that should be taken into account. Second, a fair write attribution is required. A key building block for implementing fair resource allocation is an accurate attribution of the consumption of the resource to the user. But it is hard to identify the number of writes consumed by each workload in consolidated settings. Finally, a write control knob is required. We should make each workload consume only allocated writes, but this is not feasible in storage systems because storage must serve all writes. By putting together the solutions for the difficulties, we present a lifetime management framework. Using the framework, we compare various fair-looking write allocations. Specifically, we evaluate the impact of such allocations on the workload performance. From now on, let us investigate the difficulties and our solutions one by one. To allocate writes, we need to estimate write demand of each workload. And one obvious type of writes is the ones each workload directly issues. We call them host writes. And predicting the number of host writes is easy. For example, we can refer to write intensity in the near past. However, garbage collection is another major write contributor. GC relocates data device internally, which incurs a lot of page writes. We call them GC writes. Therefore, to estimate the write demand of a workload, we should take both the number of host writes and the number of GC writes into account. Unfortunately, predicting the number of GC writes is non-trivial. This is because the number of GC writes a workload generates is determined by its allocated over-provisioned capacity. This figure illustrates the flash capacity allocated to workload A. In addition to the user capacity where workload A's user data are stored, an additional empty space called over-provisioned capacity is also allocated. Here, the more OP capacity is allocated, the fewer GC writes the workload generates. Therefore, a write allocation must come with the corresponding OP allocation, which is to divide total OP capacity to all consolidated workloads. To estimate the number of GC writes under varying OP sizes, we employ an existing analytical model. Second difficulty, fair attribution of resource consumption is key to fair allocation. In our context, write allocation indicates the division of total available writes, whereas the write attribution is the division of already consumed writes. Unfortunately, write attribution is non-trivial in consolidated settings. Let us compare three different scenarios. In the first scenario, workload A is executed alone on a flash device. In the second scenario, workload B is executed alone. In both the cases, each workload can have the entire OP capacity. The total number of consumed writes is the sum of the number of each host writes and GC writes. In contrast, in the third scenario, workloads A and B are consolidated, and each can have only part of the entire OP capacity. As a result, the number of GC writes increases, and in turn, the total number of writes also increases. Then how can you attribute the increased number of GC writes to workloads A and B? To answer this question, we propose to employ Shapley value, a classical concept from cooperative game theory. Shapley value is a tool for distributing the total gain generated by a group of players participating in a cooperative game, and its distribution is known to be fair. The payoff for player I is calculated using this equation. S indicates all possible subsets of the original cooperation set N, excluding the player I. The first term indicates the expected gain a subset S and player I together make, and the second term represents the expected gain a subset S make. So the difference between the two terms stands for the contribution of player I when he or she cooperates with the subset S. And all such contributions of player I are averaged with some weights. Then how can you apply Shapley value in our problem context? Cooperative players are analogous to consolidated workload. Then the total gain can be mapped to the total number of consumed writes in a negative sense. Also, the payoff for player I can be the number of writes attributed to workload I. Here's an example where two workloads A and B are consolidated. To calculate the number of writes attributed to workload A, two cases are averaged. One for age contribution when A is executed alone, and the other for age contribution when A cooperated with B. In the same way, to calculate the number of writes attributed to workload B, two cases are averaged. One for B's contribution when B is executed alone, and the other for B's contribution when B cooperates with A. Finally, we need a way to enforce a write allocation. That is, each workload should not consume writes beyond its allocation. We consider two Flash use cases. First, Flash can be used as main storage. In this case, all writes must get serviced from Flash. So write allocation problem is a moot consump. Second, Flash can be used as a read caching or write buffering layer. In this case, writes can be rejected from Flash because such rejected writes can get serviced from next layer main storage, which can impose some performance penalty. Therefore, we study our write allocation problem in the context of Flash cache and buffer layer. Specifically, Flash works a read cache and write buffer, and hard disk is in the next layer as main storage. When workload issue writes, they can get serviced from Flash with short latencies, and if needed, writes can be redirected to hard disk with long latencies. Using this write redirection, we can control write consumption of each workload. When the number of consumed writes is smaller than the number of allocated writes, all host writes can get serviced from Flash, and their service times are short. Note that this includes GC writes as well, device internally. We also assume that writes are flushed to disk in the background. In contrast, when the number of consumed writes goes beyond the number of allocated writes, all host writes are redirected to the next layer disk, and their service times become longer. However, normal host writes and normal GC writes get serviced from Flash. By putting all elements discussed so far together, we present a lifetime management framework. We target a period in time of relative workload stationarity. We assume that total write budget that can be used during this period is prescribed by device operator, and workload consolidation scenario does not change during this period. At the beginning, write allocation and the corresponding OP allocation are made. Write allocation is the division of total write budget across workloads, whereas OP allocation is the division of total OP capacity across the workloads. In the middle of the period, write attribution is performed periodically. Total writes consumed so far are attributed to the workload using Shapley value. As a result of the write attribution, if workloads whose allocated writes run out are detected, further writes from such workloads are redirected. by the end of this period. We compare four fair-looking write allocations. The first that comes to mind is partitioning OP evenly. Specifically, we allocate OP evenly across workloads, and we estimate the write demand of each workload based on the evenly partitioned OP. The estimated write demand would be the number of writes allocated to the workload. However, this simple allocation may not be feasible, since the sum of write allocations of all workloads can be larger than the total write budget. An alternative is partitioning OP to achieve maximum fairness division of total budget. As in the even OP partitioning, we first allocate OP evenly and estimate the write demands. Instead of using the write demands as write allocations, we apply maximum fairness division of total budget using the write demands. Finally, we repartition OP such that the allocated OP leads to the write allocation made above. The third one, called IJO-WAF, is partitioning OP to equalize write amplification factors across users. Write amplification factor is calculated by dividing the total number of writes by the number of host writes. We find an OP partition such that the resultant write amplification factors are equalized across workloads. Then we estimate the write demand of each workload based on the allocated OP partition. Finally, we use Shapley value in write allocation, assuming that the total budget is already consumed writes. We apply Shapley value to division of total budget. In calculating the expected writes of subsets, we use IJO-WAF method to partition the OP in each subset. We implemented maximum fairness, IJO-WAF, and Shapley value mechanism using MATLAB. And we implemented a consolidated cache with our lifetime measurement framework using disk simulator. So write allocations made from the MATLAB program are given to the simulator, and the simulation results are used for write attribution in the MATLAB program. We need to evaluate the fairness in write allocations. In our framework, write response time of a workload is determined by the number of redirected writes. Motivated by this, we evaluate the fairness using the difference in write response times across consolidated workloads. The closure write response times across workloads, the fairer allocation. Read response time of a workload is determined by its read cache hit ratio, which is out of our interest in this work. Since even OP partitioning may not be feasible, we compare maximum fairness, IJO-WAF, and Shapley value. Here, we show one representative consolidation scenario where four individual workloads are combined. Individual workloads have write intensities and access patterns. Left graph shows write response times of the four individual workloads under three different allocation strategies. Values are normalized to the case where all writes get serviced from flash, so there's no write redirection. Right graph plots fraction of redirected host writes of the four individual workloads under three different allocation strategies. From this graph, we can observe that Shapley value allocation is the fairest. Write response times of the workloads are closest to one another. This is because the Shapley value allocation equalizes the fraction of redirected host writes. In contrast, other allocations fail to equalize fraction of redirected host writes by allocating too many writes to some workload while allocating too few writes to the others. Let me summarize this though. We view flash lifetime as a critical shared resource that needs to be fairly partitioned across workloads. In doing so, we face various challenges. First, we need corresponding OP allocation. As GC also consumed writes, and the number of GC writes is determined by the allocated OP capacity. Second, we need fair write attribution. As the number of writes increases in consolidated settings, we apply Shapley value in the context of write attribution. Finally, we need write control knob. So we target flash buffering layer, and writes that are rejected from flash can be redirected to the next layer hard disk. We evaluate various fair-looking write allocations and confirm that Shapley value-based allocation is the fairest. Thank you.